Okay, so part 2, I'm going to change it up a little bit from what's in your instructor guide, or hopefully I've already changed your instructor guide to reflect this. But anyway, this is what we're going to do for part 2. So you are going to ask students, all right, what could we change in our simulation that would change our results? So let's think about this in terms of the natural world. What things could change from what we simulated, okay? And then have them talk about it amongst their groups. So first put it to the groups. Okay, talk to your neighbor. What things could you change in the simulation that would represent a change in the environment or change in real life that would cause maybe the outcome of this to be different? So give them time to think about it, walk around to the groups and talk to them. And then you're going to bring them back and you're going to make a list on the board. All right, and some things that we could change, well, we could have it so that the color is not heritable. Meaning that blue ones can have pink offspring and orange ones can have yellow offspring and whatever. All right, so that's something you could change. What else could you change? You could change the number of offspring. And we could do two things there. One, we can make it only one offspring instead of 3. Now they should be able to see that our population is going to decline very quickly, but will it change the color distribution that we get? Or 2, you could do like 10 offspring. And obviously you're going to put down whatever they suggest, but I'm just giving you some suggestions here. We could do it with our eyes closed. Would that make a difference? Or vice versa, we could do it without looking away. So you could actually target the dots, all right? And see if that changes. What are some other things you can change? Oh, you could start. I'm just going to erase my graph here. You could start with all one color of dot and then make them reproduce their own color. That one's pretty obvious what's going to happen. You could change your background. And you could either change the background right at the beginning and compare it to what you saw before, or you could change the background with every round. Change the background, and see what it does to your distribution. Okay, so those are some of the ideas, and they may come up with other ideas. You could do it standing on your head. You could do whatever. You're going to just have them pick something, and then each partnership is going to pick one of these things, and they're going to redo the simulation the same way. So they're going to start again with 10 of each color. They're going to go through 3 rounds. Now this one's going to be a little trickier. If you can keep your class together so that you can dim the lights, that would be great. But if they sort of get apart, you're just going to have to, I mean, you can do it with the lights on, it's just not as effective. But it would be nice if you said, okay, everybody pick your thing, discuss it with your group, decide what you're going to do, get it set up, and then let me know when you're ready. We're going to dim the lights. So it would be nice if they stayed together and they do 1 round, let them reproduce, 2nd round, let them reproduce, 3rd round. And they're only going to graph their 3rd round. And that's on their student guide. They can graph the 3rd round, but also have them graph it on their little boards. And have them graph it next to the 3rd round of their first simulation that they did. So they should have 2 graphs on their board. The simulation they did in the first part where we did it normal, and then the simulation they did when they changed something, so that they can compare. And their job is to figure out what changed and why. So let them go through the simulations, and then when they get their 3rd one, they graph it and then say, okay, what changed and why? And let them have time to talk about it in their groups to figure out what it is that changed. And once they've had time to do that, you can have a group discussion on the board about the postulates. All right, so what you're going to say is, all right, well, so why did your distribution change? And for each one, they should be able to tell you, and I'm going to erase this so we can talk about it, what changed and why. And this is what you're going to use to introduce the postulates of natural selection. Postulates being what things have to be true in order for natural selection to occur. That's what a postulate is. All right, so let's look at a couple of these. So let's say that the color was not heritable. What do you think their distribution will look like? Well, chances are they will get a distribution that does not at all look like their environment. Okay, so they went from having a distribution that looked very much like their environment to a distribution that's just all over the place. So then you would ask, okay, so why didn't your population evolve to its environment? Why didn't natural selection happen? Well, one of the things that has to be true, so these are postulates, one of the things that has to be true in order for natural selection to take place is that the variation must be heritable. Okay, so then you're going to go to the next group. What changed in yours and why? So let's say somebody did the number of offspring. Now, if they did the one offspring only, what they might see is that colors that did match the environment okay went extinct just because there weren't enough of them. Or the whole population went extinct. Or they ended up with only one color at the end because just by chance, that's the one color that survived. Okay, and that's what you'll generally see. If you don't see that, you might help them to see that that's what they would see, but let them come up with it. So, well, we saw that we only ended up with one color, but that's just because we didn't have enough offspring and they died. They went extinct. Okay, and so, okay, so if natural selection is going to take place, we have to have a lot of offspring to choose from, right? We have to be able to maintain the population, and so that's another thing, that the organisms have to reach their biotic potential. Okay, they have to be able to reproduce to the maximum amount, so we have lots of offspring to choose from. And so you might have a brief discussion about biotic potential. So what is a human's biotic potential? So that's like, what's the absolute maximum that we could reproduce? So in humans, you can have a baby about once every year to 2 years, depending on if you stop ovulating when you're nursing. And so our biotic potential is about one baby every 2 years. Now, do humans reach their biotic potential? In some countries they do. In the United States they don't come anywhere near, right? And in Europe it's even worse. And so as a consequence there's less of us too, but humans are sort of a weird case because we control a lot in our environment. But we still are under pressures of natural selection. But that's the idea, that if we have a really small population size, you're much more likely to be susceptible to genetic drift, where you're just going to randomly fluctuate because it's a small sample size, rather than having natural selection take place. Okay. Now let's look at the opposite of that. If you did 10 offspring, then even if one of the colors is like really easily selected, they're still able to reproduce a ton. And so what students might see with lots of offspring is that a lot more colors survived. And that's just because there were tons of offspring. So in that case, you didn't quite get the selection that you got before because too many people survived. Too many individual mice survived. And so with that one, what the postulate that, remember, let students come up with and say, so what has to be true for natural selection to take place? And they might say something like, well, you have to have less individuals, or you have to have some kind of cap to how many individuals can be there. And that's exactly right. There has to be something limiting. You have to have limiting factors. Because if we're going to say it's survival of the fittest, and really it's reproduction of the fittest, sorry I'm standing right in the way of that, you really have to have some that don't survive, right? If everybody gets to survive, or just about everybody, okay, then natural selection doesn't take place. You have to have some kind of limiting factors. Okay, and there's other ways to get to this limiting factors if they chose to prey on less of them, and that only 50% died, or only 25% died, or nobody died and they just reproduced again. That would be another thing you could try that would show limiting factors. Okay. So let's look at eyes closed, or without looking away, where you're actually targeting one color. You just decided to choose a color. All right, but eyes closed, if we had our eyes closed and we picked, what do you think they're going to see? And they should see a totally random distribution. Has nothing to do with the background. So then you're going to ask them, well, why didn't your population evolve then to match the background? And they're going to say, well, because color didn't matter. There wasn't any one mouse that was more fit than another. So one of the requirements is that you have to have differential fitness. Differential, wow, that was an R. Differential fitness. So there have to be some that are more fit than others. If there's not one more fit than another, then you're not going to see this distribution. So let's say these are mice and they're living on an environment, but our predator is a snake that hunts by sound, or by vibration, right? Or by smell. If that's the case, are we going to see a distribution of colors that match the environment? Well, of course not. Because whatever the limiting factor is has nothing to do with their color, or whatever the fitness factor is has nothing to do with color. Okay, so there has to be a difference in fitness between the individuals for natural selection to occur. Okay. This one, let's say, without looking away, so if they actually said, we're just going to pick all the green ones, then their color was not actually important, that people were just seeing it and they were choosing what they wanted to. So it's the same idea, that the environment and the color had nothing to do with it, so they didn't get selected that way. All right, so starting all one color, so that's another one. So if you start all one color, let's say they chose all green dots on this red-pink environment. Well, obviously at the end they're going to have 100% green dots, and they don't really even need to go through the 3 replications, but make them do it anyway. And so you ask, well, why didn't yours evolve? Well, there was nothing to evolve. There was no variation. Aha, exactly. So you have to have, there must be variation, and ask them, where did that variation come from? Did they change because of the environment, or was there variation there? Well, the answer is yes. There was variation there, so variation by mutations. All right, so there has to be variation already in the environment. If there's no variation, then the organisms will not evolve. They will not evolve by natural selection. All right, so there has to be variation. And then this changing the background, right? So that if you change the background in between, then they keep adapting to one, and then they have to adapt to a different one, and they have to adapt to a different one. So if you get this environmental change, that's actually going to cause them to go in different directions. Let's say that the environment never changed. After you get your distribution, so this is a little tricky, right? After you get a distribution, if you never change the environment, you're just going to stay that distribution forever. Okay, so there have to be differences in the environment that will cause it to shift in allele frequencies. But in this case, changing the background, it is going to shift them one way and shift them another way and shift them another way. But if you change the environment, you're going to get a different distribution, and that's what you want to point out. Is why didn't your distribution look the same as it did with the other one? Well, I had a different environment. There were different selective pressures. So you do have to have changes in the environment for something to shift out of Hardy-Weinberg equilibrium, for frequencies to change. And then you're just going to sum it up. At the end, it says, the natural selection causes favorable variations to increase in the population and unfavorable variations to decrease in the population. All right, so you'll just have a summative discussion, and you might bring in examples. Feel free to Google examples of natural selection. You could talk about the jackrabbits and their really tall ears. You could talk about the cryptic species that they totally match the flower that they live on, bugs, or that birds match the environment that they're in. You could talk about elephant tusks and poaching and what that's done to natural selection. You could talk about, in human populations, the CCR delta 5 mutation on the white blood cells that's making people immune to HIV, and it's changing frequencies over in Africa where they've got a lot of HIV. There's a whole bunch of applications of this that you could talk about in lab to sort of get your point across. All right, so in my next video I'm just going to run you through the homework, and then we're done.